Well, yeah, so everybody, thank you. Welcome. Thank you for coming to Groom's first webinar of 2026. We're hoping to have a couple more this year throughout the year, so keep an eye out. My name is Matt Del Turco. I'm the marketing manager here at Groom who put this together, but it's all going to fall on the shoulders of Ryan, Andy, and Jason to give you guys all this great information. So just a couple details real quick. Everybody's mic is going to be disabled for the entire presentation. If you have any questions throughout or at the end, please use the Q&A tab. Go ahead and put your questions in there, and then we will address them, at the end. And then at that point, if I have to enable your mic so you guys can talk to the presenters, I'll go ahead and do that at that time. The webinar will be recorded, so anybody who is registered, whether you're here or not, will get a copy of the recording so you guys can pass it along to your colleagues and things like that. So yeah, let's go ahead and get started. Jason Sabatic, our South Central Technical Sales Rep, is going to start us off. He covers Texas, Oklahoma, and Arkansas. So, Jay, go for it.
Yep, thanks for everyone being here. The main topic for today's webinar is maximizing the lifespan of your CO catalyst. Next slide, please. Yep. So I just want to start off with a little quick overview. I'll be handling part one. So yes, I'm Jason Sabatic, Technical Sales Representative for Groom Industrial in the South Central region. I'll be covering catalyst system life cycle, rejuvenation versus replacement cost, causes of CO catalyst issues, whereas Andy Toback, Principal Engineer from Environex, will be covering part two. That will cover catalyst chemistry, catalyst performance, and CO rejuvenation wash studies. The third part will be covered by Ryan Esposito, Vice President of Engineering for Groom Industrial. He will be covering CO catalyst timeline, rejuvenation process, as well as on-site support. Next slide, please. So I wanted to give a quick background of both Groom and Environex. I know most of y'all will probably know who we are, but just going through that real quick is Groom is a nationwide provider of turnkey services for the power generation space. We've been in business for over 50 years. We actually started back in 1969. Started as a painting and coating company, and throughout the years have grown our service line through both organic growth as well as strategic acquisitions. Since we're talking about catalyst services here today, all of our catalyst maintenance services have been approved by all the major OEM catalyst manufacturers, and even some of the services have been developed hand in hand with some of these major manufacturers to be able to do best practices with maintaining these catalyst systems. With Groom, we currently offer 5 main service line divisions. First is catalyst maintenance. Second is mechanical services. Third is painting and coating. Fourth would be our industrial cleaning, so our vac and water services. And then fourth would be our explosive cleaning services, including our patented HRSG fin tube cleaning service, Kinetic Clean. So going into Environex, they are a independent, non-biased SCR or catalyst system experts. Their engineering firm does, well, in 2025, they were able to support over 1,000 catalyst samples tested. They specialize in catalyst systems across different industries, technologies, systems, and fuel types. So they are the industry leader when it comes to catalyst systems and the science behind troubleshooting how that and how to properly maintain these systems as well. So some of the services they offer, including lifecycle management, catalyst testing, which they have their lab locations out of Philadelphia, Pennsylvania. They also do support facilities with SCR and CO design services. For instance, if you're coming up on a replacement and you don't want to go with a like kind catalyst or even the same manufacturer, they're actually able to help you in that decision-making process. They also support AIG tuning, And they also provide consulting and troubleshooting services. One of the cool things they actually offer every year, and I believe it's once or twice a year, hosted around different locations around the country, is their training, their short course training program. It's a great 2 to 3 day event where your young engineers or your system owners for your catalyst systems can actually go to that program and learn more about the actual science behind the catalyst and best practices. So going into part one is our CO catalyst life cycle and costs. So as you can see here, there's 3 different pinwheels with catalyst life cycle. The one that we're really here to talk about today is the CO catalyst life cycle on the left here. Each one of these pendants on this life cycle pinwheel here are typical maintenance items or steps in the life cycle that you'll experience throughout the life of your CO catalyst. Typically first starts off with some testing to try to get a good idea of what the useful life is of the catalyst and help project on when replacement or rejuvenation will be needed. Next is the cleaning and the repacking as your 2 main common maintenance items to maintain performance of your catalyst. Next would be system modifications depending on the operation of your unit, and if that changes, possible system modifications might be needed. But then kind of at the end of the road of that life cycle is either a catalyst rejuvenation or a replacement. So that's kind of what we're here to talk about today is how to make the determination when replacement is necessary or when CO catalyst wash rejuvenation is actually on the table and a viable option. So starting off with the cost breakdown, the comparison between rejuvenation wash and replacement. The cost is quite drastic between the two. For instance, a new catalyst for an estimated size of like a frame size unit is about $750,000. That price is actually might be a little bit shocking for some of y'all if y'all haven't done a replacement in a while, just because the main driving factor to your new catalyst is the platinum price per ounce, which, as a lot of you may know, the gold and silver markets have been going absolutely crazy, whereas platinum is kind of part of that upswing as well. So it's a cost that keeps going up and is kind of the main driver to that new catalyst cost there. Whereas CO catalyst rejuvenation cost is actually somewhat fixed, right? And we have an estimated price of about $250,000, give or take, on the size of the unit, and what will be needed. So right there is an instant potential savings of $500,000 if rejuvenation is a possibility to increase the performance of your CO catalyst. That savings all includes while staying in compliance, but does not include potential loss generation or derate due to CO catalyst performance. So in case of your CO not performing very well, you have to derate to maintain in compliance. That derate and loss generation adds up very, very quickly. Another huge advantage to utilizing the CO catalyst rejuvenation wash is just the lead times of a new catalyst. Just a couple years ago, it was probably in the neighborhood of 2 to 3 months for replacement CO catalyst, but those days are long gone, and we're now looking at lead times of 10 to 12 months. And I'm sure if any of y'all have seen the SCR catalyst lead times, those actually have been growing as well. Rejuvenation wash lead time can be pretty much performed instantaneously once the unit comes down offline. And with that, it's a pretty quick turnaround time. We can get you back up and running relatively quickly, but there's really no lead time items besides a few logistical planning items that Ryan Esposito will be talking about later. As you can see on the right here, this is a graph kind of just comparing replacement costs and rejuvenation costs compared to turbine size. I think the main takeaway here is that even though the smaller simple cycle units that are 40, 60 megawatt range, even though the cost savings is not as great as possibly say your larger J and H class units, there still is significant savings of estimated about over $150,000. So it still is a very viable option, at least on the cost savings side, even with smaller units. So how do we actually get to the determination of either needing to replace or do a rejuvenation wash? Well, that is actually checking all the boxes of the system issues that could be causing bad CO performance as well. One of those is actually physical blockages or fouling. I'm sure if y'all have maintained these catalyst systems for a long time, you've probably done some cleaning. But the reason why cleaning is so important is that this fouling creates high DP across your catalyst, but also reduces the exposed surface area of the catalyst, basically giving those CO molecules less of an opportunity to go through the oxidation reaction. One of the contributing factors why fouling can be detrimental to your system as well is that when these smaller insulation particles or boiler rust actually gets caught into the catalyst itself due to the flow of the gases in the HRSG, these particles are going to try to work through the catalyst foils, and on its way out, there is physical erosion to the wash coat that can occur. Uneven flow distribution can also be an effective or can also be an adverse effect, especially to your downstream equipment like your SCR or CO. And for instance, if you have a large portion of your catalyst that is fouled, say 30%, then you're asking the bottom 70% that is not fouled to pick up the slack of that 30% while trying to stay in compliance. So you're basically asking the catalyst to do more with less, which, depending on the age of your catalyst, most of the time takes you out of compliance. Talking about high differential pressure, obviously it's reduced turbine output, but we have seen, if this becomes neglected and not addressed, we have seen that high fouling and high DP can cause frame or module damage. These are avoidable costs by keeping up with your annual maintenance or routine maintenance, and these costs do add up very quickly and can be detrimental to your unit. You can go to the next slide now. One of the next common causes of CO performance issues is bypass. Bypass is basically areas in your catalyst that allows the gases to take the path of least resistance. So that's either a bad seal around your panels there, or holes in your catalyst, missing modules, and typically that will show up in your operating data as a low CO conversion, so high CO at the stack. But also you won't see anything. You won't see an increase in DP or a reduced increase. Whereas, when you're looking at fouling, that's when you see high DP, that's typically a good sign that needs to be cleaned. So one way, bypass can be occur inside your unit is gasketing failure. So typical setup of these CO panels is that there is some type of gasketing around the perimeter of these CO panels. When that becomes damaged or liberated, it will cause a decrease in the seal from the panel to the actual framework of the catalyst itself, but also has the opportunity to cause looseness in the panels of the retention system. So with that, if those panels do get loose through vibration and thermal expansion, things of that nature, these modules actually can become liberated. So if you do see anything like that, it's definitely something that needs to be addressed. The third cause of CO performance issues is deactivation. But before we get there, one of the things I want to mention is that if we're ever on site or you have the opportunity to get in there and do an inspection, I would take advantage to do that. For instance, if we're there on site for a catalyst cleaning, if that catalyst cleaning does not address the root cause of your CO performance issue, if you stack in, say, pulling a sample for testing, or call Environex or your local groom technical service representative to come out and do an inspection of your system. We can go ahead and check these boxes and get further down the process of the troubleshooting, equation there without having to delay or waste time of coming back down online to grab a sample and stuff like that. So I definitely want to put that out there is take advantage of your opportunities to get as much information about your catalyst. So if something does not go as planned, we have the information to be able to, in real time, to be able to help with the troubleshooting aspects. So going into the third main cause of CO performance issues is deactivation. This is towards the end of life of the catalyst, and there's really two avenues deactivation can go down. There's wash coat failure, which is most likely physical erosion on the wash coat due to age, where there's really no way to get back from that, and that's kind of leading towards replacement. But one of the main topic we're here today is talk about rejuvenation, which addresses the poison accumulation on your catalyst. So if poisons are accumulated, it can decrease the performance of your catalyst there, which a rejuvenation wash is aimed to combat. So with that, I will turn it over to part two with Andy Toback at Environex to talk about the chemistry and kind of the science behind how CO catalyst performs.
Thanks, Jason. Yeah, so as Jason alluded to at the end of that slide there is if you see a back pressure issue, you come in with the correct intent of cleaning your catalyst. If you grab a sample while you're in there and the catalyst cleaning didn't address your high stack CO issue, testing, and in this case, the whole cause of this webinar is you can wash a CO catalyst. Don't get this idea for SCR, but for a CO catalyst, the contaminants can be removed with a chemical wash and to a varying degree of success. Matt, if you'd advance me, please. First, I need to get into how a CO catalyst works and how it can deactivate in order to be able to discuss the payoff, of is your CO catalyst viable for this wash procedure? So oxidation catalyst, which we're going to call CO catalyst today, is the oxidation of CO with oxygen in the stream to form CO2. And in your VOC reactions that I have there on the bottom, you're looking at propane, propylene, and formaldehyde as examples, but essentially you're converting these unburned hydrocarbons into CO2 and water, which is also what your combustors are doing. So this is a second chance for those. On the right, you see what we refer to as a light-off curve. And I'm showing them in three different ways because what is interesting about oxidation chemistry is you can learn what the issue is with the CO catalyst by the shape of that curve. So if you look at the blue line on this graph, I'm showing CO oxidation, so removal percentage as a function of temperature. The fresh line is represented in blue. The fouled catalyst, the catalyst that has the active sites blocked, and if you could stick with me here, which I don't really know if you have a choice, I'll get into fouling on our next slide. But to continue this one out, there is a big difference between what is poisoned permanently and what is fouled and can be removed. So if you look at the shape of the curves between the blue and green line, you see that there is just the maximum conversion potential across each of your catalyst temperature ranges is overall lower. So what are those ranges? Well, your combined cycle range is shown there below 650, and that's probably a lot of the attendees today are operating their oxidation catalyst in that zone. Where an oxidation catalyst would love to operate is in your simple cycle non-tempered zone, which is 850 plus or 800 plus. Your red line, this is not necessarily today's topic, but if we if we test a CO catalyst and the shape of the curve looks more like your red line, then that's an indication that there is a more permanent contaminant at play. If you'd advance, please, Matt. So I showed you what typical performance looks like. Now I'd like to talk about how this catalyst deactivates. And everything that I want to talk about is what you can't see. So Jason did a great job of discussing what you can see and the procedure of removing what you can see. You know, they go in with their procedure of back blowing, vacuuming the material off the catalyst at pressures that don't disrupt the wash coat material, which I'm going to get into what that is here in a minute. That's all of what you can see. So now we're going to go microscopic. And if you look at the image, the graphic I have on the left side of your screen, this is how this CO catalyst works. You have CO or VOCs and oxygen coming through that catalyst channel. The paint or coating material is where all of the reaction takes place. So if you think about what your catalyst looks like, it is a metal or ceramic foil with a paint or wash coat that is adhered to it. And the coating, that wash coat, is very thin compared to the amount of metal that you have there. And that makes a lot of sense. The metal's an inert. There's no reaction happening there. But all of the reaction, and it's quite a bit of reaction. The reaction rates on your CO catalyst are so good and so fast, it's a fraction of the size of your SCR. I'm pretty sure if you have a CO and SCR catalyst and looked inside your unit, that has occurred to you. Wow, you know, this CO catalyst is so small compared to the SCR. This is why. It's a very active material. And it works by, and then if you can follow along the illustrations I have on the top here, that first photograph is what you see with your eye when you look at the front of a CO catalyst. Now, if we take a piece of this CO catalyst and look at it in a bird's eye view, this is a herringbone design where you can see if you're the gas path going through one of these channels, you could see it's a mildly tortuous path. That just aids in mass transfer. Mass transfer is the governing reaction rate of the overall reaction rate of oxidation chemistry, because the reaction rate to oxidize something is so fast. Think about rust. All you want is for rust to not occur on the fender well of your car or on the metal fence that you had painted. That is a reaction that wants to take place. And in the exhaust itself, it wants to take very fast. So the actual limiting step here is mass transfer. And what is that? Well, if we go to the next photograph on the right, this is a microscopic image of what that wash coat looks like. So microscopically, something that to your eye looks flat and smooth is actually very, I'm going to use the word fluffy here, because it has a lot of surface area, because you want that gas in less than a second to be able to go through this wash coat, which I'm illustrating here, into one of these pieces of the wash coat, which is also very porous, which I'm denoting on this bottom left photograph that is labeled fouling blocks mass transfer. And then each one of these pores I'm representing in the last photograph where I'm calling it poisoning eliminates active sites. I should probably have changed that to contamination, because what I'm really showing here is that your big three for oxidation catalyst contaminants are zinc, sulfur, and phosphorus. These are what are reacting with your platinum sites. And this is what we're targeting in what we are hoping to remove. Next slide, please. So how do we test catalyst? We just talked about how it deactivates. So now I want to talk about what happens when we get a sample and how we determine if we want to use this particular sample to determine viability of catalyst wash. Well, here's an example of your typical test equipment to test the viability of a CO, or test the performance of a CO catalyst sample. You have, this is Environex's setup, but many are very similar. You have control of your simulated exhaust gas, which we dial into the exact rate depending on if this is coal at oxygen starved conditions, you know, somewhere between 1 and 3 to 5% oxygen. Your recip engines, which have a little more water than maybe your combustion turbine, and then your combustion turbine, which in a simple cycle application, we'd operate at close to 15% oxygen because that's where they operate. Or if you want to talk about your combined cycle application without tempering air, something closer to 12 or 13% oxygen. We have the capability to dial all that in. And then after you heat up the bulk of your air, add your water, then we dope in the CO, NOx, and ammonia that we would use for whichever sample we're testing. It would be all three if it was dual function. In today's conversation, we're talking about just CO. So then the simulated exhaust, hot exhaust, and CO goes through your reactor, and then very similar to your SEMS system, we measure what that CO coming out of the reactor is. We know what we put in, we know what's coming out, we have a removal. What you see on the right is a typical oxidation catalyst test result. Here, this sample tested very well, and we're looking at conversion efficiencies that are over 90% across the entire temperature range. The minimum conversion shown in the dotted red line is directly from input at the plant. So in this case, this plant has a 40 ppm inlet CO, and their stack limit is somewhere, you know, in the single digit range, 5 or 6. This is information that if we have, is very helpful to determine, all right, you know, in this particular case, and you can see in the operating range of 750 to 800, so this one's simple cycle. In this particular case, this is a catalyst in very good shape. And that's the intent of this slide, is I'm just showing you what a typical result looks like and how this stock result will look. Before we depart here, now if you go back, Matt, before we depart, what we need in order to accurately test this catalyst is we need to know the fuel flow, or we can calculate the exhaust flow from that, the operating temperature that your particular application is subjected to, the catalyst volume. That one is huge. It is, if Groom or Environex haven't been to your site and you just send a sample button or sample radiator, we need to know the volume in there. The ratio of the exhaust flow to the catalyst volume is a very important catalyst testing parameter. And if we don't get that, then it's harder to test the catalyst at your exact bulk flow conditions, both in terms of cross-sectional area and linear velocity. And the geometry, we get that on our own when you send us the sample. Next slide, please. So what do results look like when a wash is not viable? I had these slides reversed for the entire week leading up to this presentation, because you would think you'd want to see the good results first, but then I just couldn't figure out how to segue to Ryan. So we're going to start with catalyst test results where a wash study is not recommended. So bad news first, then good news, right? If you look at the left here, the reason why we even attempted this wash study was, if you look at the conversion requirement in the red dotted line, the sample test results are right there. The blue line is right at where the design conversion is. And in this particular case, there was some elevated CO at low load. So we said, all right, let's look at catalyst wash. We hit this one with, and this is based on what the chemical analysis looked like. We washed this one with a mild pH acid solution, something like lemon juice pH. And that's kind of important because I want to reiterate how these are not like strong acids required in order to make such an effective wash solution, though this slide isn't really telling you that. Sometimes we've noticed that warming the acid bath up to about 130 F will make a larger impact. And so in this particular case, because the contaminants were mostly sulfur, we tried that. And then we also, because there was some silica on there, we first washed one of the samples in a base solution and then rinsed that material off and then washed it in an acid solution, which does have an effectiveness when there are multiple types of contaminants that are present on the catalyst surface. And then we retested all of those samples and we didn't get any desirable results. So while the bulk of this webinar is going to focus on how good a rejuvenation is, it's really important to note that blindly washing a catalyst may not get you the results that you want. The study is so important to determine if this is a scalable feature. In this case study, the one I'm showing on the left, there was no change made. If you look on the right, the first thing I want to note is that this catalyst performed terribly. If you look at the y-axis, we're between 0 and 60% CO removal. Now, all of you have requirements that are at least over that 50% line. And most of you, if you've tested catalysts before, you've seen your results above 75 and mostly above 90% removal. That's a pretty normal design. This one was in dire straits, and it was integral to try to determine whether we can wash this catalyst during the outage, which is another perk that I think Ryan is going to touch on more. But if we get in the beginning, if you have a major outage, that's got more than 20 days to it, and we take a sample as soon as the unit's cool enough, we can determine if a catalyst wash is successful, and you can come out of that outage with a catalyst that has a lot of its original life restored, which I'm going to get to here in a minute. But before we go, on this right slide, I want to note that there is a DI water wash that we performed on this sample. And the reason why is there are a lot of times where it is an easier disposal cost if we're not using an acid. So in this example, the location of this facility made the water wash a more desirable wash. And in this particular case, if you look at all three of the results, none of them got you near the minimum design conversion. So this is another case study where, unfortunately, we had recommended replacement as opposed to the success of wash, which is what I'm going to show now, if you'd advance, Matt. So this is I get to end on a very positive note, but these are some typical wash study results that are amazing, right? So if you look at the slide on the left, this is again a really poorly performing oxidation catalyst. There was a heavy amount of both phosphorus, zinc, and sulfur on there. And the reason I kind of grouped the three of them together is if you find a lot of zinc and phosphorus together, it's usually lube oil infiltration into your duct. And sulfur is just inherent in your fuel. It's happening. It's everywhere. And even though the value is below the tariff, it has increased significantly from the early 2010s to now. We've parked on the pipeline and have taken data with like a 1 or 2 year campaign. And like I said, even though it's still well below the tariff, it's still double what it was previously to 2010, 2011. And double still means that double the amount of sulfur is getting into your HRSG or your duct or your recip engine, as long as we're talking about natural gas as the fuel. If we're talking about diesel, it just has more sulfur to begin with. But if you look at the chart on the left, the dotted line is saying, all right, well, we need 69, 70% CO removal. And the sample that we tested was doing, about 52% at best, at closer to the higher end of its operational window. So in this case, we did both a acid and hot acid wash, and look at those results. That's back to near fresh. So we've waited kind of until now to give you the reality of how well some of these washes can work on your catalyst. Is we could get you pretty close in some cases to fresh performance. So if you wanted to revisit the economics that Jason brought up in the beginning, we're talking about bringing you back to new at a fraction of the cost without having to wait, if it works. So, I mean, we just came off of a slide where I discussed a few of the examples where it didn't work. These are the ones that did. And if you look at the one on the right, while the DI water didn't work, this was another case where it would have been really nice if the water wash would have worked. And in some cases they do. They just didn't for the ones I decided to show today. And we're a bit time limited. I can't take the entire webinar to show 15 years of catalyst wash studies. Although if any of you know me, know I would absolutely love to do that. I'm going to wrap my end up here with this slide on the right, where both the hot acid, the base and the hot acid did an almost identical job. And then because of that, you wouldn't pick the base acid because that's just 2 chemical washes. You would pick the hot acid for this one. And again, you're looking at well above the performance requirement. And in this case, again, near fresh returns. So where I'm going to end is the wash study worked. And I rarely get to say this in this industry because there's always an exception to every rule. But every time that we have washed the catalyst in our lab and then Groom has field washed that catalyst, our procedures are a direct scale up of each other. We've taken samples after the field wash and compared them to the lab wash, and they have always been identical. There is so rare a time I get to say the word always here, and I get to say it now. So I'm going to come off my win and hand this over to Ryan, because now that you can see, if you're on this story with us, now that you can see this works, Ryan's going to show you what that looks like once we scale this up at your plant.
Yep. Appreciate that, Andy. Yeah, so I'm going to try to, you just got a lot of information from Jason, a lot of information from Andy, and I'd like to go through kind of the practical application, what it's going to look like from a plant standpoint, someone trying to plan for a rejuvenation. And I think the best way to do that is going to be to go through an example. So Matt, if you could hit the next slide, I'm going to jump right into it. And say you're operating your unit, it's right now, right? It's the winter run, and you're starting to notice some elevated CO at the stack, but you're not really sure, what's the cause, and you're trying to, do the right thing. And you're going to be proactive. So you decide, okay, let me perform a mechanical cleaning, an air cleaning, and we'll do some inspection on the seals and pull a sample for testing, right? So we can kind of tackle both the system issues and catalyst issues and try to differentiate what's actually happening in the unit. So you have you're operating right now, you have your planned outage in April, but that's the game plan going in. So this timeline on the right here is kicked off like kind of right at that point. So say that outage you have starts in April, you pull your sample, you send that to Environex right away, and they can start testing. So even before the outage is coming to an end, that catalyst is already in queue to be tested. So the typical turnaround time that you can expect from the catalyst testing is around 6 to 8 weeks. So in 6 to 8 weeks, so say you go in there, you clean it, maybe you start back up, you got marginal improvement, but you're not 100% back to where you want to be. But you have that kind of in your back pocket, like, hey, we're getting the catalyst tested. If it is a catalyst issue, we're going to find out kind of what the extent is and hopefully what the mechanism of deactivation is and kind of figure out next steps from there. So that would be kind of an ideal game plan as far as I'm concerned for kind of how to attack that situation. So 6 to 8 weeks, you get your results back, and it comes back that, hey, it is a catalyst issue. We've identified the mechanism of deactivation, and now it's time to decide, is a rejuvenation study a viable option or not? So that will be part of that initial catalyst test, will be to say, hey, this is a good candidate for a rejuvenation study. We don't know if the rejuvenation or catalyst wash, I go back and forth between wash and rejuvenation, but if that's a good idea or not. And if it is, then we can recommend that, and then you can make a decision on whether you want to go ahead. So also pulling the sample during the outage, if Environex is doing that, then they'll pull enough sample that if it does need a rejuvenation study, they'll already have that on hand. You don't have to take the unit back down again to pull another sample, so you have more to test for the wash study. So say you want to do that, you can expect in about 4 weeks that you'd get the results from that rejuvenation study. So 6 to 8 weeks for the test, 4 to 4 weeks approximately for the wash study results. And it's going to be, at that point, you're going to have the go, no go plot that Andy was just going over, saying, hey, this did an excellent job, or hey, don't waste your money and try to wash it because that wash isn't going to work for one reason or the other. So that is a critical point in this process right there. So say you get the good news and you can rejuvenate it, then you don't have to have all that extra time. So the timeline in red in this plot, I just have this going from April out to December. This is kind of best case scenario for a catalyst replacement timeline currently. I wasn't trying to go for dramatic effect and give you some of the other lead times that we see. Depending on the catalyst manufacturer and the design and several other factors, you could be upwards to a year. I think Jason had mentioned a typical 10 to 12 months. That is pretty typical. So this is kind of a best case scenario replacement compared to a rejuvenation. Now, if the great thing about the rejuvenation, if it is possible, then you can perform that basically right away. You get that news, and if you choose Groom for that, we're going to ask for a little bit of time to get our manpower and equipment and materials and all that kind of lined up and make sure that we're fully prepared for when you go into outage, to make sure it's a successful project. But other than that, it's really whenever you have time. If you wanted to do it in your next scheduled outage, however that works, it does give you some flexibility there and get you back up and running where you want to be right away. So that's kind of the difference between the replacement and the rejuvenation options as far as timeline goes and what you could expect there. So as far as outage time needed, I have some timelines there on the left based on unit size. Obviously, smaller units, smaller time needed, bigger units, more amount of time needed. And those are shifts. So we can work around the clock. So if you wanted to talk about, days needed, cut those in half. So, 4 shifts for your 40 to 60 megawatt units, and, talk about 8 days for your larger frame unit. So that's kind of just to give you a ballpark of how much time we'll need for a full scale rejuvenation. Good, Matt. Okay, so now that we know the timeline, if the rejuvenation is successful and we're gonna plan for the actual outage work and the full scale wash, just gonna go through kind of step by step what to expect, what kind of things would be great to be thinking about before the wash is performed, what to expect once we're on site and performing the wash. So the first thing is mobilization and training. So obviously we'll have a safety plan. We're going to want to know what other work is going on around the area, all the typical outage work planning process there. But as far as mobilization and staging for this type of work, we typically ask for an area roughly 50 feet by 50 feet. Doesn't need to be square, also doesn't need to be 50 feet by 50 feet. What we usually do is we'll go through like an aerial or a satellite image with you and try to find out, pick some real estate out, where we try to get as close to the doors of the unit as possible. The idea for us is best practice is to minimize handling of the catalyst whenever possible, right? You don't want to overhandle catalyst in any way. So if we can get it near the unit, it also saves on time, makes it a little bit more efficient. So if we can grab some real estate around there, that's great. As you can see, we'll have secondary containment set up, primary containments, tanks, liners, and we can get all of that staged before you come down, so we're ready to kind of rock and roll as soon as the outage is moving along. The next thing is scaffolding. So some units, and I'm sure a lot of you are aware for your plants, but it is something to consider. The CO catalyst modules themselves are typically hand carried. So they'll be moved in and out of the doors towards the bottom of the unit. And sometimes there's considerations for how do you get those, down inside the unit and then down to ground level. So if there's, scaffolding needed, exterior, interior, those are things that we're going to want to think about and make sure we're fully equipped for while we're doing the work. Good, Matt. So once the mobilization is complete, scaffoldings, we have access to the catalyst. The next thing is going to be pulling the catalyst modules and actually performing the wash. So a couple of things that I like to think about the actual removal and replacement of the modules themselves. There's a couple of different frame designs. Just be aware of what frame design you have, drawings, pictures. If during your outage you can grab pictures, or if we're in there, we'll grab pictures. But just to see the general condition, the arrangement, sometimes there's been modifications from when the drawings were made. We just like to see kind of what to expect when we're going to be inside the unit. Hardware and gasket considerations. So there's two main frame designs or variations of those are extremely typical. One is the studded frame design, where you have, if you were to remove all the modules, it looks like an array of picture frames in your unit. So each module will fit into an individual picture frame, and then the sides of those picture frames will have studs welded to them, and washers and nuts will be used to retain the modules in place, to hold them in place. So typically those washers are designed to hold the module, but you also don't want the washers to be so oversized that you're blocking catalyst area. So those are usually pretty specific to the units. So when we're doing a rejuvenation or even a replacement, anytime you're taking the catalyst modules out and reinstalling them, you can typically reuse those washers. The condition of the studs, it varies significantly from unit to unit. So if you know your unit and it's an older unit, or maybe you have a newer unit. The newer units, sometimes you can take all of the modules out and there's no issues with the hardware, and you can go back in and it's no big deal. But some of the older units, maybe it's wear and tear. You could see, I think on average, I'd say we're somewhere in the range of like 5% of those studs need to be replaced. But just something to be aware of, and have some studs on hand, have a welder on hand to make sure that you reinstall them and not be waiting on any of that in real time. The other design to be aware of is the retaining bar design. In that type, the modules are stacked kind of in columns, usually 5 or 6 high before you get to a frame member, another horizontal frame member, and then you go 5 or 6 more high from there, higher. And the retaining bars are held into the vertical supports by nut and bolt hardware, which are typically killed by the typical design calls for them to be killed, which means you need to cut them and replace all of them. So just another thing to be aware of. You're going to need a significant amount of hardware if that's the case. So just some things that we'll take a look at and understand before we get on site, so we're fully prepared for that part of the process. Now, the actual rejuvenation, you can see some images here from that process taking place. Usually there's multiple tanks. You have a wash tank, you have a preparation tank, and a disposal tank, a waste tank. So we'll use those to manipulate the wash solution. Obviously we prepare the wash. The wash solution specifically will be taken directly from Environex's report. And that's when Andy was talking about mimicking the lab scale results to the full scale results. That's kind of where the magic happens, is right in that step. So you removed all the catalyst modules. Now you're performing the wash, and that'll be performed for that amount of time that's designated. And then you can pump down the tank, and after that, the catalyst modules are good to go. So after the wash is performed, we'll refill the tank with D-min water, do a rinse, pump that out, and then you have in the top right picture in this slide, you see the drying process, right? Critical step there is the catalyst drying process, and that will happen before the reinstallation. So once the catalyst is reinstalled, obviously you want to make sure that you have the proper gasket on hand. Make sure all the seals look good. You don't want to have any system issues. You just corrected the catalyst issue. So you want to make sure that you're all aligned there. Final check, inspection, and then you're good to go. So the last things are scaffold removal. You'll now have waste in a waste tank that we have to take care of. We don't really have a preference as far as how the waste is handled. We do it many times, but also sometimes plants prefer to handle the waste themselves if they have their own protocols, and we just take that on a case-by-case basis. Once that's done, then we can demobilize, and it's been a successful project. You should see immediately upon starting up, reaching steady state, that the lab scale results match what you see in the field. So I think that kind of takes us through the whole process there. This is a summary slide for kind of things that could be coordinated between Groom and the plants for lay down area, scaffolding, just things to talk about, things to kind of cross check and see who's providing what. Demon water, where is that located on the site? How are we going to get it to the wash area? We can talk about power requirements, the supply of the chemicals, when are they coming? How do they need to be stored? And then we just talked about the waste management. So I think that kind of summarizes the project from a full scale perspective. I know I kind of ran through that pretty fast for how much work that is to plan and execute one of those types of projects, but I hope that was informative for how a project would go. So with that, I think we're going to enter a Q&A section here. I'm going to pass this back to Jason, but I know everyone's unit is unique and everyone has a unique circumstance. So if there's any particular questions anyone has that we didn't touch on, feel free to reach out to any one of us here, after this call, and we'd be happy to help you. So with that, we'll move into the Q&A section.
Yeah, and how we're going to handle the Q&A. Always welcome to write a comment inside the Q&A section. On the Teams option at the top there, or if you would like to, you can raise your hand, and then we'll go down a systematic approach, and Matt Del Turco will open up your mic so you can ask your question that way as well. It looks like Kyle has a question. Matt, can you please unmute him? All right, Kyle, I think you're unmuted. I think you're just muted on your end.
Okay, can you hear me now?
Yep.
All right. Hey, good morning, guys. Thanks for the presentation. Really appreciated it. Does the long-term performance of the rejuvenated catalyst match new catalyst? In other words, if we went the rejuvenation option, would it have the same effect as replacing the catalyst?
Andy, do you want to handle that one? Because it kind of goes into the science behind it.
It depends. Sorry, this is going to probably be my answer for everything. Here's what it depends on. So if the contamination event was a one-time event, then we would expect the deactivation, like let's say it's a bad seal, and you get a slug of lube oil onto your CO catalyst. We wash it off, but you also at the same time repaired the source of your zinc and phosphorus. We would expect the CO catalyst deactivation rate to be as slow as it was before that one-time event. If it is a chronic sulfur problem, it is going to deactivate at the same accelerated rate as the deactivation that you saw previously. If it is a newer contaminant, like let's say you have a catalyst that's been in service for 15 years and now you're seeing the deactivation rate increase and it's because of something that you can't mitigate, we wash the catalyst, it's going to go back to that same level. So we would expect in almost all cases for the deactivation rate to be similar to what it was before. And it would start with wherever you were able to restore the fresh performance from. So if we weren't able to get, the graphs I showed were great examples because this is a presentation promoting CO catalyst rejuvenation, but there are some other in-between cases where, let's say, fresh performance is 95% CO removal and the wash gets you up to 90, then you wouldn't have that same timeline you previously had because you didn't get up to your exact fresh performance. Does that work, Kyle?
Yep, that answers it. Thank you very much.
Perfect.
Yeah, and Andy, I think that kind of opened up, a thought in my mind as well. Can you kind of just briefly touch on that the CO wash is actually able to be performed multiple times in some cases, where it's not, a kind of a one and done thing?
Yes, I can think of an example where we've been washing a CO catalyst every year from 2010 to 2014, and in 2013 we had to switch from DI water to the acid solution in order to get the performance increase that we needed. In your smaller recip applications, this is just a way of life. So if anyone in this audience is from your like compressor, gas compression, or smaller recip power gen, natural gas power gen, you're used to just having 2 sets of catalyst and washing a set and keeping it in critical spare to replace like right before your emissions compliance test or something like that. So there's a little bit of A, a little bit of B there.
Yeah, and then we did have a question out in the chat from Jeff Myers. He asked, "Who owns the waste disposal? Part of the project or is site responsibility for disposal?" And our West Coast representative, Christina Juarez, answered it pretty well. She said it's site specific. It could be handled by the plant or by Groom. So it's really up to each facility, right? If y'all want a total turnkey solution there, we can handle the disposal. But if your EH&S department has some reservations about that or would like to handle that themselves, no problem. That could be up against the plant as well.
Jason, there's also a question there in the Q&A from Brian Stowell.
All right, going to that right now.
We can.
Yeah, and then Brian asked, is it possible to get a copy of the slide deck to review? Yes. Matt, are we going to be actually sending out the presentation, or are we just going to be sending out the recorded version of the webinar?
I believe we will send out both, but I can confirm that with everybody. But you definitely will get the recording. And there's also a question right below that too, Jason. You had another question right below that question.
Yep. Okay. So yeah, Brian, we'll be able. This webinar will be posted. I believe probably maybe on our website or in some of our socials. But we will make sure that you have access to this to go back and review or share it to somebody who wasn't actually able to attend. Brian's next question was, can any of the items you discussed besides, oh, sorry, I just had something pop up and block that. Can any of the items you discussed besides the bypassing cause stratification during our RADA testing?
Brian, I unmuted your mic. Brian, if you'd like to speak to Jason, you can go for it. You have to just unmute yourself.
Yep. Andy, do you want to talk about that? That
Are you seeing CO stratification, or is this NOx stratification?
Actually, on separate units, we're seeing both CO and NOx. Some are showing CO and some are showing NOx stratification.
So then it's interesting. That's the exact flow of this webinar. Can you confirm that the CO catalyst is clean and that there's no like big obstructions, because that's honestly the first box I would look at.
Yes, we had a third party come in, do an internal visible inspection. We also sent off a sample to get it analyzed, and there was no large obstructions. We weren't showing any bypassing. Everything looked fairly good inside internally, and also the catalyst testing came back, stating that we still had a large amount of lifespan left on the catalyst. So,
Okay. So my direct answer is, can bypass cause stratification? Yes. But it also sounds like what level of CO stratification are you seeing? Is it like a percent or two, or are we talking like half the duct is in the low digits and the other half is 10 or more? I'd like to get some better context of how much stratification that you guys are measuring to be able to start pointing in a more useful direction.
okay, yeah, it's minimal, 1 to 3%. But like I said, it may cause issues with our rata testing coming up, so we're trying to troubleshoot all areas and figure out what's causing this.
Well, here's how we do this this rundown. It's all about checking boxes. So you just checked a lot of them, and that's great. I like the approach that you took to handling this problem. Is the catalyst good? Yes. Is the catalyst dirty? No. Is there bypass? No. So then you get to my next assumption, which is this a simple cycle application?
No, we're combined cycle.
Oh, now we get a mystery. Could it be a duct burner issue?
That's
Because
that's what we're looking into and trying to figure out if that's the issue.
think about how much mixing you have from your CO catalyst all the way down to your stack, which I'm trying to point at the stupid background, but it's not working. There are multiple rows of boiler in there. Every half inch, every inch of pressure drop is mixing. So if you're measuring a problematic stratification at the stack after it's gone through 10 static mixers, this is figuratively, this is a big problem. So I think that maybe you want to get a stack tester in there and do some post duct burner pre-CO catalyst traverse testing, or just preemptively get someone out to tune the duct burners, because that's where I would look next based on how you have already been approaching this problem, which is a mirror of what I would do. You did everything right.
All right, thank you.
Yep, thanks for the question there. We got one more question here from Randy Bullock. He said that I believe Andy had mentioned about ensuring enough sample material is pulled to perform an adequate wash study. How many buttons / coupons, etc., are needed?
Well, I guess I'll just answer that one too. So if we're talking BASF 2-inch radiator or a 3-inch button, then one of those is enough. If we're talking about a 1 to 1.5 inch pre-cut core sample, like your Johnson Matthey style, I'd like 2 of those, ideally 3. If we're talking about catalytic combustion or Synergy or Miratex sample radiators, 1 of those is adequate.
Yeah, so Randy, I guess it depends on the actual style of CO catalyst you have, and but most of them are typically just 1 sample, besides 1 or 2 of those manufacturers. We have another one from Andrew Schaefer. What was the drawback associated with an acid wash versus a water wash?
Material handling. And Ryan, I think you're a little more suited to answer that.
Yeah, no, totally agree. If the water wash is a viable option, it's the easiest to handle. It's the easiest for a lot of reasons. But and the only drawback is really convenience and cost, I would say. Um, those are the big kind of differences between those. So we try to use the simplest or the easiest solution as long as it's a viable solution. You know, you start with your water, then you go to acid, and then if an acid base is better than the acid, then you go to that. You kind of go in order of complexity, or just more things you have to worry about and take care of the more complex the wash gets.
And Ryan, when we're talking about water wash here, we're talking about still pulling out the panels out of the unit, or is that an in situ?
For the comparison in this, I would call it a water wash, pulling the catalyst out and washing it. The in situ wash is another option, kind of for different reasons. So I don't know if that would be a direct comparison.
Yeah, perfect. Well, that is all the questions we have in the chat here. Does anyone have any other questions? Please feel free to either raise your hand or type them in. I guess we have a little bit over, but we can always stay back just a few more minutes in case somebody else has one. Oh, looks like maybe one of them came in here. Robert Zeiss, or Zeiss, sorry if I mispronounced that name. He just submitted a question. He said, percent water wash versus acid wash. Which one do you typically see?
Hi, Bob. So normally, I would say 20 years ago it was more water wash, and now we're seeing a accelerated percentage of acid wash. I'm only getting a few water wash results that would justify using it over the acid. And like Rye said, it's usually where there is more of a waste disposal concern, where we hope that the water wash will get results that are viable compared to the acid. We hope the water works, and when it doesn't, we're prepared. And recently, we're getting less water washes that work. I also think that the sulfur tolerant formulations need a little more power to restore some of that lost performance than what we were all working with 15, 20 years ago.
Yep, so we'll give another minute or so in case anyone's got any other questions. Don't see any in the chat or in the Q&A, open Q&A section. I do not see anyone's hand raised. Oh.
Oh, that was me. I don't have any questions. I'm just not good at computers.
Yep, Jeff, appreciate the kind words there. But other than that, I think we're. Oh, Andrew Schaefer just came in with another one real quick. He's got, was phosphorus a proper target for acid wash?
Yes.
And Andy, I guess as far as the, determining which type of solution works, I know it's somewhat of a trial basis, but is there any type of trend depending on what the poisons are, on what that you've seen certain different type of solution would work? Because I know I always get questions, hey, I got phosphorus on my catalyst, or this other type of poison on my catalyst from my testing results. Is there any type of trend there, or is it kind of just more trial by error?
Mostly, not always. The acid wash does a good job on phosphorus and sulfur.
Yep, and Andrew, I think your mic's open right now in case you want to have any follow-up on that, but if not, all good.
I'm good. Thanks, guys, for the presentation.
Yep, appreciate you being here. I guess with that, I don't see any more. So this is kind of the last call here. But if something else pops up after we get off this webinar here, feel free to reach out to myself, Andy or Ryan, or even one of your local technical sales representatives on the groom side. We're more than happy to take any of your questions or set up any one-on-one individual meetings to review any specific concerns that y'all are seeing with your systems, or if you're looking for an inspection, don't hesitate to give us a call.